So now we will get a bridge, get a link with what we saw before in the weeks before in terms of dealing with linear discriminant models, but parametric methods. So this is somehow relating the things that we saw with parametric models and multivariate models with the kind of approach based on gradient descent that we are presenting this week. So with parametric classification, if you remember well, we kind of ignore the evidence here in terms of base rules, and we are using often directly the likelihood of a given data according to class X CI and its prior probability of class CI. So this gets us some kind of discriminant function that we can use. Applying the log on that, which is perfectly fine because the log is not changing the order, it is a monotonic transformation. And if we care only about the value of H in terms of comparison with the other H's for a given classification task, we apply the log on the likelihood and the prior. We got something like log of P of X given the class CI, log of the prior. If we assume that Px given Ci correspond to a multivariate Gaussian distribution, what we saw last week. So it's basically that thing here. We can get as equation that other thing. So Hi of X is that. So we are just applying the log over the multivariate Gaussian distribution function plus the log of the prior, and we have a new H that is that thing here. And we can approximate the prior directly from the data using like the number of samples from class CI given the total dataset size. And we can approximate the mean vector that way. So the mean vector is approximated from the data, and the covariance matrix is also estimated from the data. So these are things that we saw 2 weeks ago, and so as such, I will not repeat how we get this, but it is exactly the same thing. But we can go further with this. We can get into the situation where we will share the estimation of the covariance matrices. So we will share them. So we have a general covariance matrix that is the same for all samples, but we keep different vector means for each classes. And then the function H goes that way here. So it is basically that function because the rest is kind of unchanged. And developing this further, so this equation, we get into that version, which is basically X transpose inverse of SMI, so the mean vector for class I, plus this thing, which is invariant of X. X is not in that part on the right, so we can consider this as a constant, while this thing is depending on X, because we have X transpose at first. And we can show that this is basically a discriminant model, so a linear model, I would say. So this is a discriminant, linear discriminant here that we have with Wi transpose X plus Wi0, where Wi is equal to the inverse of S times Mi, and Wi0 is equal to that big thing here. So looking at this, we can see that the linear discriminant with we obtain is that one. So that in 3D, we have this kind of plane that is cutting the space in two, with on one side the blue dots and on the other side the red dots. So these are the two classes. This is a linear model, basically. What we can do is that we can go further along the way for developing what we have with two-class parametric classification. We know from parametric models that we choose class 1, for instances, when the posterior, the PCI given X, is bigger than the posterior for C2, the PCI given X. And otherwise, if it is not true, then we can just assign X to C2, because we are in the case of two classes. So knowing that necessarily for two classes, PCI given X plus C1 given X plus PC2 given X is equal to 1. So mixing out things, we can get like the PC2 given X is equal to 1 minus PC1 given X. That's kind of basic. And if we just define a Y as equivalent to PC1 given X, just say that X is equal to the posterior of class C1, we can get, the rule is to check at PC1 given X versus PC2 given X and assign the sample to class 1 when PC1 given X is bigger than PC2 given X, replacing this by the Y value that we define here. We got something like the Y is bigger than 1 minus Y. And dealing a little with the playing with the equation, we got into something like, okay, this rule, this rule here is equivalent to say, is W divided by 1 minus, is Y divided by 1 minus Y greater than 1? Or if we apply the log on both sides, which is perfectly fine, we've got something like, is the log of Y divided by 1 minus Y positive? And this thing here is interesting, and we can define this as what we call the logit function. So we just define a f of y, which is the logit function, which is looking at the value log of y divided by 1 minus y. This can be really useful for that. So let's say that we know that y is equivalent, is defined as, just looking at this thing, y is defined as the posterior of C1. So if we just fall back on that and use the posterior here, we get into something like, okay, the logit function applied on that posterior is equivalent to this, which is equivalent to that. So it's the log of the ratio between the posterior of C1 divided by the posterior of C2. If we expand this, because we notice this is the posterior, we just expand this according to the base rule, we've got into something like, okay, this is the log of the likelihood of C1 divided by the likelihood of C2 for a given X, plus the log of the prior probabilities ratios between C1 and C2. Developing the equation using the Gaussian distribution, we've got that thing. And if we try to simplify a little, we've got this. This is directly in the form of a linear discriminant. And that linear discriminant, by doing some simplification, is corresponding to a W equal to the inverse of the covariance matrix times the difference between the means for the two classes. And as for the constant, we have that big thing here that is including all elements that are not dependent of X. So yeah, developing again even more that function, we know that f logit of the posterior of C1 is equivalent to that and can be stated as a linear discriminant using the W and W0 we found just before, when we assume that the data is distributed according to a normal Gaussian distribution. We can then define the inverse function of the logit. So the inverse of the logit is called the sigmoid function, or also called the logistic function. And so knowing that we have this thing as logit function, we can see that all these things is equivalent to A. So now we are looking at the inverse function. So we see that f logit of y is equal to A, then the inverse in terms of sigmoid is correspond to y equal to f sigmoid, so sigmoid function of A. And we know that A is equal to that. So if we just kind of move things around and make the manipulation, we've got something like this thing. So we know that in fact y is equal to 1 over 1 plus exponential minus A. And that specific function is really what we call a sigmoid function. So we can directly assume that, P, the posterior of C1, which is defined as y, is corresponding. So we know that y is equal to that. So we know that the posterior is equal to the sigmoid function applied to A, which is basically the linear discriminant. So it is corresponding to applying the sigmoid function on the W transpose X plus W0. And if we expand this, we've got that form. So basically, our posterior is equivalent to 1 over 1 plus exponential minus H of X, which is W transpose X plus W0. But we will, the thing is, I'm saying it is equivalent to H, but this is not right in the sense that with the developments here, that thing here is not our H. Our H is slightly different. We will get into that. So looking back, I know at this plot, which we saw at the beginning of the presentation this week, we have the same thing. You know, we see here the likelihood, and we've got here the posterior. So the PTF and the posterior class probabilities. So this is interesting because we can see that that model here with the sigmoid function, with the logit function, is a way to represent a discriminant function, a linear model. In fact, that is a linear model, but inside that sigmoid function. So basically, we have our linear model on which we apply the sigmoid function, which gave us the posterior probability. So the posterior of C1 is equivalent to the sigmoid applied to the linear model. And that is directly related in our modeling to the normal distributions. So using normal distributions, as we did with our parametric model, is a probabilistic way to fall back on some kind of linear discriminant model, but passing through the step of estimating the densities. So assuming that the densities are normal, Gaussian, well, everything boils down to a linear model if we share the covariance matrix between the classes. If we are not sharing the covariance matrix between the classes, that's something else. That's a quadratic model. But as we are using a linear model, we can use the same kind of modeling we are developing here. And this is what I will show you for the next step, the next clip.